Okay, good morning, good afternoon, good evening, depending on wherever you're calling from. Welcome to Weekly Science Review from Vetri Labs. Here at Vetri Labs, we focus on enabling implementation of electrochemical technologies at scale. Today's Weekly Science Review is going to be led by Dr. Ayyappan. Dr. Ayyappan is a research scientist at Vetri Labs. Over to you, Ayyappan. And I forgot to mention, as we are recording this, please turn the video off during the presentation mode, and then we can turn it back on during the discussion session. Thank you.
I think
You can share now.
Okay, good morning, everyone. Today we'll be going over the electrochemical detection of serotonin using tetragonal shaped zirconia oxide nanoparticles, modified carbon-based electrode. So before going in, just a brief introduction of what is serotonin and why is it very important for the detection of it. So serotonin is a monoamine neurotransmitter that plays a key role in sleep or like biological processes such as sleep, mood regulation, appetite control, cardiovascular function, and also emesis. And the standard 5-HT, so serotonin is 5-hydroxy tryptamine, so it's a short form is 5-HT. So the standard 5-HT level is about 0.25 to 0.74 millimolar. So there is two different things. So you shouldn't have either a low level of 5-HT or a high level of 5-HT. They both have different causes. So with a low level of 5-HT, it can cause migraine, anxiety, depression, eating disorder, and blood clotting, and just leading to a death syndrome. And high level of 5-HT can cause like potential fatal effects, including the serotonin syndrome. So what are the ways that literature has adopted to quantify serotonin? They've used HPLC, fluorometry, mass spectrometry, ELISA, and electrochemical method. Among all these different methods, detection using electrochemical method from the blood serum seems to be more effective, and it is also like cost effective and also less time consuming. And so there are different metal oxide nanoparticles and different materials that has been used to detect serotonin. But here in this paper, they focus on using zirconia oxide for the first time, since it's a highly stable polymorphic ceramic metal oxide. And zirconia is very high temperature stable. So at that high temperature, they can also give you like high stability and hardness because of their high strength and toughness. So depending upon the method, you synthesis the zirconia oxide, and also depending upon the crystal phase. So it has like three different crystal phase, such as monoclinic, tetragonal, and cubic. So depending upon the synthesis method and the crystal phase, it has been explored for different applications, starting from gas sensor, catalysis, refractory materials, scratch-proof coatings, and thermal barrier coatings, and also an optical coating, oxygen sensors, and also in the orthopedic implants. So in this paper, they did the material preparation. So they used a method, gel combustion method. So in this, they used zirconium nitrate solution as an oxidizer and glycine as a fuel, and used a very minimum water and stirred it for 2 hours to form a homogeneous solution. And then they were heating it on a hot plate to evaporate the extra water so it can form this viscous gel. And then they transferred this viscous gel into a muffle furnace that was already preheated to 500 degrees Celsius. Then after that, since this viscous cell is flammable, it gets fire, and then it gets combustion, and then at last it forms this white fluffy nanoparticles, which substrate, that is the zirconia oxide nanoparticles. And then they characterized it to confirm the presence of zirconia. And also on the electrode side, so how do they transform this zirconia oxide nanoparticles, ZNPCs, to electrode? So they used a carbon-based electrode method. So to know the influence of zirconia oxide nanoparticles, they did two. So one is a bare carbon-based electrode, where they prepared it by mixing silicone oil with graphite powder in the ratio of 30:70 by 8%. And then for zirconia oxide modified carbon paste electrode, they prepared it with a mixture of zirconia oxide nanoparticles with silicon oil and graphite powder in a ratio of 10 is to 10 is to 80. And on the material characterization side, so initially they used XRD to confirm the crystal phase, and what they found was it's on a tetrahedral phase. The crystal, the lattice parameters were calculated to be around 5.180 for C, and B and A were about 5.079 Armstrong, and they belong to a P42 NMC crystal phase. Next, with XRD, they used Debye-Scherrer formula to calculate the particle size, and they found it was to be roughly about 35 to 40 nanometers. And then they did the SEM characterization, and what they found out was, and from the SEM, they can see a agglomeration of the zirconia oxide nanoparticles, and they attribute that this could be due to the preparation method they employed, and they're also porous, and because in the combustion there will be gas evolving, and though they create the porous pores in the substrate. Then they did the TEM analysis to confirm the particle size, and they found it to be around 40 nanometer, which coordinates with their XRD calculated particle size. And the particles were crystallized with a mixture of spherical and hexagonal shape with from their SAED pattern. And when they did the high resolution TEM, they calculated this lattice fringes, and then they found it to be 0.31 nanometer, corresponding to the 101 spacing of zirconia oxide nanoparticles. So moving on to the electrochemical characterization. So before trying to detect with the serotonin, so they used potassium ferrocyanide to calculate the electroactive surface area of the different electrodes. So as you can see here on with just bare, which is the black line, the bare carbon paste electrode, and then the red would be the zirconia modified carbon paste electrode. And you can definitely see there is an increase in the current density. So there is an increase. So the zirconia oxide nanoparticles are very active, and they are able to oxidize and reduce the potassium ferrocyanide complex. And they found out that the electroactive surface area was about to be 0.0237 for the carbon paste electrode, and 0.0286 centimeter square for the zirconia modified carbon paste electrode. And to initially to understand the like the oxidation of the serotonin, they used it in a mixture of a PBS buffer to adjust the pH to 7.4, and we'll see why they use 7.4 pH in the later slide. And what they found out was just the bare carbon paste electrode showed a very low current response at 0.349 ohms. However, under the similar conditions with the zirconia modified, they had an increased in the oxidation potential to 0.316 volt, and also they had an increase in the current signals. And so to understand why so they did the effect of pH analysis on this setup. So they used they changed the PBS buffer to alter the pH starting from 5.8 to 7.4. And what they found out was, as they increased the pH, the oxidation potential shifted more to the positive potential, and also there was an increase in the current that they were measuring. So for this reason, they found out, since they got the maximum current at 7.4 pH, so all their electrochemical studies were done using the pH at 7.4. So to kind of identify if the reaction is indeed diffusion controlled or not, so they used CV to test the so in 10 micromolar of serotonin in a 0.2 molar buffer solution at 7.4 pH, and they changed the scan rate starting from 0.05 volts per second to 0.5 volt per second. And they recorded the anodic peak current, right? So they extracted that and plotted versus the square root of the scan rate, and they indeed found it to be linear with a correlation coefficient of about like 0.994. So this kind of confirms that indeed it is diffusion control, the electron transfer process. Then they used what is the effect of concentration on the peak current of 5HT at zirconia modified carbon paste electrode. So to identify that, they used the linear concentration from 10 micromolar to 50 micromolar. And so as they increased the concentration, there was an increase in the current that they were measuring, but with a slight shift in the potential towards the positive side. And so they extracted the IPA and the peak current and plotted versus the concentration, and they formed out the linear regression equation with a correlation coefficient of 0.9943. And so then they find out the limit of detection and the limit of quantification using this formula, where S is the standard deviation and M is the mean of the three calibration curve that they generated. So the detection limit was found to be about 0.585 micromolar, and LOQ was found to be about 0.1953 micromolar. And so since ideally when you measure it in a blood serum, you don't have just serotonin, you have a mixture of other biomolecules that can be like dopamine, adrenaline. And so they wanted to know the interference of the other components in the investigation of serotonin. So for this, they used dopamine. And as you can see, with the Zirconia modified carbon-based electrode, had a voltammetric signal well defined with peaks at 0.174 volts and 0.34 volts, confirming the separate. So the peak was separated for both dopamine and serotonin, and there was no interference. So to further identify the interference of this, they use the differential pulse voltammetry. And as you can see, for the bare carbon-based electrode, there was a very less sensitivity for corresponding to dopamine and 5-HT. But whereas for the zirconia modified carbon-based electrode, which is the dotted lines over here, the peak potential shifted towards the negative side, and there was also enhancement in the sensitivity of both dopamine and 5-HT. And this confirmed that there was no interference, even though when there was a presence of dopamine in the selectivity and sensitivity towards serotonin. So in summary, they used gel combustion process to produce zirconia oxide nanoparticles, and which had a good sensitivity and a good stability. And also and the zirconia oxide nanoparticles were in a tetragonal phase with a mixture of spherical and hexagonal shaped particles, and they would show about 40 nanometers in size. And these developed carbon-based electrode had a high detection towards 5-HT, and with an increased peak current and reduced peak potential. And they had a higher linear range of 10 to 50 micromolar with the detection limit of about 0.558 micromolar. And eventually they want to do this of testing it in like using a human serum, so it can be like less time consuming and economical since it's an electrochemical detection. So with that, I'd like to thank you all, and let's move on to the discussion section.
Thank you, Ayyappan. Questions, comments, thoughts from the team?
Like when you're reading this paper, what did you think was like the most promising application from this? Like they talked more about the study than like the future.
Yeah, so future would be like trying it in like using human serum, but I kind of doubted that it would be very efficient, because I think the ultimate aim of this paper was to use this zirconia oxide, which has never been used for electrochemical detection. But on sensitivity and detection point of, there were other materials that are far better. For example, there is iron oxide supported on like I think multi-wall carbon nanotube. They can go down to like a detection limit of about 0.05 nanomolar, so which is 3 orders of detection limits higher. So in that way, I mean, eventually they want to apply this, but I think they used like a paperwork. So just try to do a quick analysis using, with the lab setup. They bought all these from like Sigma Aldrich, just run the experiments quickly. So trying to find application for the nanoparticles is how I see this work.
So, like, it seems like a good work. Like, they just use the paste and then put it on a recessed electrode for the working electrode?
I think so. I think that's how they've done, probably.
So what is the working electrode?
Okay.
The
So, they might not know the loading then.
I didn't hear you.
Like, the loading of the zirconia nanoparticles might be a question then. Like, they fill it, like I just saw the electrode preparation. They fill the electrode and then they make it flat with the as the electrode surface. So the loading might be a question, right?
Yeah, but I think they make the paste with 10:10:80, right? So
Hmm.
they have probably a control of zirconia oxide over there.
Hmm. So the amount of material they put on the electrode is
Hopefully making it a homogeneous paste. So in
maybe
that
they
way,
might have the volume of the resist, how
mhm,
much they have done it, and they can calculate it.
yeah.
Yeah. So one thing that occurred to me is typically when I think about zirconium oxide coming from solid oxide background is as an ionic conductor. I never think of zirconium oxide as a catalyst. Did they talk about any mechanisms of the catalysis action and
No.
why it's oxidizing?
No, they did not go over that at all.
Okay,
Yeah.
okay. So it's a purely empirical study, and maybe the particle size is so small that there's some mixed, but this is not even doped, right? So typically when people dope with ceria, it can be a mixed ionic and electronic conductor. Whereas if it's purely zirconium oxide, I don't know what the electronic conductivity and ionic, maybe I don't know what the mechanism is. That's why I was curious.
Yeah, and also I mean, there is an improvement compared to carbon-based electrode, but I don't see a huge improvement. Whereas the people have just used boron dope diamond or even a glassy carbon, and they can get about like I think 0.1 or like 0.8 or zero point 0.9 micromolar sensitivity, just using glassy carbon, just functionalize it with some polymers.
Got it. Got it.
So
But so in that case, maybe the stability is a problem, right? Polymer,
mm,
how long it stays. Maybe that's why they were thinking.
mhm.
But it would be nice to have some mechanistic discussions so that people can build on it and move on from here, right? So,
Having said that, like they could have like kind of tested the reproducibility of the electrode as well, like testing it once and then again washing it and then doing the test again. Have they done any testing like that?
No, but when they mentioned the limit of detection, right, they said they mentioned 3 calibration curves. So my assumption was probably they ran 3 experiments, but they just showed only one over in the paper.
that's true. Yeah, awesome. So they have the oxidation current in the
In the reverse.
reverse.
Yeah, yeah.
So yeah, it reminds me of the very old convention.
Hmm.
Yeah, yeah. That's just a minor thing that I noticed.
Yeah, it was quite confusing. I mean, I have seen in old papers that
Right.
having it in that convention
Correct,
maybe,
correct,
and this
yeah.
is very new. I don't know why they adapted that
Correct.
way of interpreting the data.
Any other comments, thoughts, questions? If not, thank you all. And Ayyappan, what are we talking next week?
Yeah. Okay, so next week we'll be discussing about copper doped zeolitic imidazole frameworks, ZIF8, as a single atom catalyst for oxygen reduction reaction in alkaline media.
Excellent. Thank you, Ayyappan, and thank you all for joining us for the weekly science review. If you'd like to lead a discussion, please send us an email at info@vetrilabs.com. Thank you all.